This video presents my own personal take on the problem-solving techniques that are introduced in our textbook. Our textbook uses a strategy that the author calls IDEA, IDEA. Cute? Yes. Most modern textbooks have a similar cute acronym to help you learn to make this part of your approach to science a consistent part of your approach to science. You need to have your own personal problem-solving strategy that you use consistently every time you encounter a new problem. This is a good one. I really like it. It's similar to what I've always done my entire life. Step one is to interpret, to classify the physics, what physicists call the physics of the problem, the underlying theoretical ideas. D is to develop. That includes drawings, includes the equations, and it includes doing algebra. It doesn't include using your calculator. It includes doing algebra to simplify expressions and solve them. Only when you get to the evaluate step do you use your calculator. This is something you really need to work on learning how to do. Finally, A, assess, which is to check your answer and learn from your answer. That's a really important thing that a lot of students don't appreciate the first time through. Now, I'm not going to repeat everything from the textbook. You need to read the introduction to the IDEA approach on page 8 and think about each step, and in each chapter, as you encounter a new example type, follow the details of how that IDEA approach is applied to that particular kind of problem. My goal here is just to put a particular emphasis on the skills you probably didn't learn if you ever did learn how to do word problems in an algebra class. The things that I see students most commonly forget to do. So these are my points of emphasis. 1. Start at the beginning. That may sound obvious, but many students do not want to start at the beginning. They want to grab an equation that's actually the solution to a problem that someone else has done, something that someone gave them, something that they found on the internet. You will not learn anything by doing that. Exam solutions must start from a basic equation, not something derived from it. If it's been derived in the book, it's not one of the basic equations. Don't memorize it. It doesn't do any good to use it because you'll lose all of the points that are required associated with the required derivations starting from that equation. Your homework should start not only with the basic equation, but your identification of the problem type, your interpretation of it. You don't want to really take time to do that in an exam. You can do that in your head. But if you do that in each homework problem, it'll help you classify each problem into a particular category. And then if you list the relevant basic equations, learn them quite thoroughly and quickly learn how to sort out which equations to start with. If you have come to me with a question about your homework, or if you come to someone in the Learning Commons with a question about the homework, or another student with a question about the homework, the solution is not to use Google or DuckDuckGo to find it. You need to ask yourself the same questions I'll ask you. My first question is always, what kind of problem is that? Kinematics? Net force equals ma? What kind of problem is it? And what equations are you planning to use? What equations were you trying to use? You should expect the same question from a tutor in Learning Commons and anyone else you happen to study with. If you don't know the answer to these questions, that's where we need to begin, is helping you to be able to answer those questions yourself. After that, we can work on algebra. Number 2, define all variables, all symbols that appear in the various equations. You want a list of all of the known quantities, each one associated with a symbol that appears in an equation, and the unknown quantities, the things that you don't know, that maybe you want to solve for or might need to be used in conjunction with, say, 2 equations and 2 unknowns to solve for the one thing you care about. You always want to know what your goal is, what your unknown is that you care about. But you also may need to know about some other ones, and you always need to know what you know. And by the way, physicists use the term variable for any symbol, even if that symbol happens to be a constant, even if it's known in the problem. We prefer using symbols over numbers because it's always easier to use a single letter than it is to write down a 16-digit number. Next, what equation should I use? Again, my first question is always the same. Can I see your list of equations, the equations that you're using to do this class of problems, this topic? You should have a short list of the basic equations for the current topic. For example, for kinematics, There's 5 of them that are enough to do everything that we do in the first 2 weeks of the semester. And later, sometimes only 1 equation and a couple of definitions. So when you're in a particular chapter, there's only 1 equation that you need to learn that's new. And if you always start from that 1 equation, you have very little to learn except how to solve problems. Step 3, do algebra. This may sound obvious, but it isn't. Most students want to plug in numbers. They're used to plugging in numbers in math classes. However, the math classes have single-digit integers in their problems. We have 3, 4, 5-digit numbers. We might have something that's a number times the sine of some angle that ends up being a 10-digit number. You can't solve equations if you have to copy over a 10-digit number every time you rewrite the equation. If it's Vx naught, call it Vx naught, and only at the very end do you plug in the numbers for that symbol. Then you use algebra to solve the system of equations for the unknown that you want in terms of the knowns that you have. Do algebra, then plug in your numbers and calculate. And again, this may sound obvious, but many students do not use their calculator efficiently. I'll see people writing down half a dozen different numbers along the way. Multiply A times B and write it down, then multiply that answer times C and multiply it times D. You should be able to evaluate the entire expression in 1 step. Write down your final result, substitute the known values in, and compute it in 1 pass on your calculator. If there's a previous result you need, it should still be in the answer register, so you just hit the ANS key to pull that back up into and put it where it needs to be. Re-entering numbers is a huge mistake and leads to all sorts of errors as well. Is your answer wrong? Well, whatever you do, don't start guessing. That will not lead to a productive solution to your problem. First thing you want to do is check every number against the ones in the problem, or maybe a constant from the formula that's used in the formula that you've got. If those are right, and for that matter, if you've copied your final answer correctly into the computer program that checks it, then go back and calculate the final expression again. Go back to your final equation, put the numbers in it. Maybe be careful to use the numbers directly from the original written version of the problem rather than from your own notes, and see what you get. If you get the same wrong answer, then one of 2 things is wrong. Your algebra was wrong. Your equation is wrong. Your starting equation might be right, but your algebra was wrong. Or you hit the wrong key. Sometimes you hit the same wrong key every time you compute something. In that case, sometimes recalculating in a different sequence will help. You go back and check your algebra. If your algebra is okay, then your starting equation was wrong. Go back to the interpret step and ask for help, or ask for help. Don't just run your numbers through some number scrambler, hit puree and try to have them compute with them in a different combination. You've got to start from a particular equation that applies to the physics and go from there. More often than not, students have made a minor calculation error somewhere or have a copying error somewhere and end up going off in a wild tangent when they were already within 5% of the right answer and just need to fix one little detail. If you don't understand the physics, don't understand where to start, then ask a question. Don't just make up random numbers. 5. When you're done, units and rounding. You should write your calculated answer to 5 or 6 sig figs so you can check your calculation and your rounding separately. You want to be able to recompute something and know that you got the same answer to 5, 6, 7, 8 digits. After you've written that down, then write your final answer separately, round that final answer to 3 or 4 sig figs, write the units, be sure you've got parentheses as they're needed, and check all of it before you enter it into the computer or before you box it as your final answer on an exam. So, closing thoughts. Don't just read an example in the book, or don't just watch an example in class. In the book, they'll skip steps in the algebra that you need to work through on your own sheet of paper because maybe you need some practice on algebra. And do the same thing with examples from class. I might skip a step or 2, or you might not have had time to write it down. Classmate might have written it down. Maybe between you and a classmate, you can figure out what algebra connects one equation to the next and maybe why I followed that particular process. You also have some other resources. The solution to odd number problems in our book appear in the Student Solution Manual in great detail. The Student Solution Manual, available in the Learning Commons, has the full IDEA solution to every odd number problem in our book. It's extremely useful. It's almost like a collection of examples. And finally, there's also other textbooks in the Learning Commons. They're on a shelf by the study rooms, and maybe you can find an example or a different way that something is explained that's different from the way I explain it, different from the way our textbook author explains it, that you find helpful. And to close, are you learning? Your goal for each chapter or two is to see that every problem is the same. Once you start learning physics properly, you'll see that every problem of a particular type is really the same problem, starts with the same equation, and often has the same process that follows it. And if you succeed in that, you'll still have that skill next year when you need it, because you're going to need to use all of these things when you take mechanics next year as an engineering student.